Good morning, everyone. We are Group 6 and I'm Justin. Today, I'm presenting the paper Deep 6 Max Pushing the Limits of Mathematical Reasoning in Open Language Models. The challenge addressed in this research is twofold. Large language models struggle with mathematical reasoning due to its complex logic and long multi-step derivation. While models like GPT-4 and Gemini Ultra perform extremely well, open resource model lag significantly behind. The goal of this study is to develop a domain-specific LLM that greatly improve mathematical reasoning and approach the performance of model like GPT-4 on high-level benchmarks such as max. Therefore, the authors choose to use a large max corpus and a new RL algorithm called Group Relative Policy Optimization. The DeepSeek Max model is built from the DeepSeek Coder-based V1.57b model. It's trained on the DeepSeek Max corpus, a massive size of max-related token mined from Common Core using a fast-tag classifier. The training pipeline will starting from max pre-training, then supervised fine-tuning with problem-solving data and GRPO to further enhance reasoning. The interesting part in this approach is the authors use GRPO to improve max reasoning while normally it's used in-game. The paper introduced the DeepSeek Max corpus, 120B tokens that outperform prior max dataset in quality and size. This resulting the model beats largest model like Minerva on key benchmark. Also, a new RL method GRPO improved performance by using group relative advantages instead of a critic model, enhancing max reasoning ability and efficiency. This model also evaluated on several key benchmarks, including max, general reasoning, and formal mathematics.
I'm Ijun. So on this slide, I'll explain the pre-training stage of DeepSeek Max. So the main goal of the project is to build a domain-specific large language model, which is the DeepSeek Max 7b, which is specialized in mathematical reasoning. So instead of increasing the model size, the authors focus on two things: high-quality data and large-scale math-related tokens. So to achieve this, they extend the existing DeepSeek coder-based version 1.5 model using the 120 billion max-focus tokens. So the setup is also shown as here. The base model is 7B parameters with trained on 500 billion total tokens. The data mixture contains max data, GitHub code, ASCII papers, and common crawl text. So we also train using the AIT306 optimizer, which is a peak learning rate of 4.2 E-4 with warm-up and multi-step decay, and a very large batch size of 10 million tokens. So overall of the training is, rather than making the model bigger, they make the data smarter, especially on max data. Next is the data collection and pipeline construction. So this slide shows how the team collects the max-specific data from the web. The pipeline starts with a small but high-quality seed data, which is the Open Web Max. Next, they train a fast-text classifier to auto-detect whether a web page contains mathematical content or not. So they use 500k max pages and 500k general pages to train this classifier using 256 dimensional vectors, 3 epochs, and n-grams. After that, they apply the classifier to Common Crawl, which contains around 40 billion HTML pages. The pages are scored, and those that look the most mathematical will only keep. The most important part is the iterative refinement. So after each filtering round, they discover new math-rich domains like mathoverflow.net, which the human annotators label new max URLs, and the classifier is retrained and the process repeats. So after 4 rounds, they collect 35.5 million math web pages, which corresponds to roughly 120 billion tokens. So finally, the dataset is decontaminated. This prevents leakage from benchmark like GSM8K or MAX by removing any text that overlaps with benchmark questions or answers. So the result of this pipeline is the DeepSeek Max corpus, which a clean, large, multi-record math datasets is much bigger than previous math corpora like MathPy or OpenWebMax.
Hi, I'm Hao Liang, and now my part is about introducing the possible policy optimization and group relative policy optimizations and how GRPO matters in large language models and its benefit. This is introduction of possible policy optimizations. So when PPO improves the policy while keeping updates stable, it uses a probability ratio to compare new and old policy and applies a clipped objective to prevent overly large updates. And this is some function of the parameters. And this page introduces a procedural overview of possible policy optimizations. And I will introduce the group-related policy optimizations. Unlike PPO, the GRPO removes the value models, making training much more efficient. And the advantage is compute using group normalized rewards, which allows GRPO to capture richer feedback. And GRPO also use KO divergences constraint to stabilize updates, similar to PPO but applied in a group-based framework. And this is a comparison between GRPO and PPO. PPO use individual symbols and clipped objectives, giving good local stability. And GRPO intends PPO by using group-based advantages, removing value networks and adding KO regulations, result in high stability and lower cost. And this is a procedure code overview of GRPO. And this is a key benefit of GRPO in large language models. First is better reward signal stability. Second is improved alignment quality. Next is enhanced training efficiency and stronger generalizations. And last is a smooth integration of PPO framework.
I'm Ping Kwan. So in the first experiment, the authors compared a DeepSeek map corpus with other existing corpora. They trained a 1.3B model on each and evaluated it using few short COT on math tasks. As shown in the table, DeepSeek math consistently outperformed the others with the steepest learning curve, as shown in the figures, delivering better results on both English and Chinese math tasks. Next, DeepSeek Math Base 7B was trained on the DeepSeek Math corpus and outperforms all other models like Mistral and L Lemma on GSM 8K and Math. It also performs well with the tools as shown in the table and in formal reasoning tasks. So as you can see in the table, the model proves that the math-specific pre-training enhances reasoning and proof abilities. Then next, DeepSeek Math Instruct 7B fine-tuned on 776,000 math instructions, perform well on GSM 8K with 82.9% and Math with 46.8%, surpassing many larger models. When tools are added, performance improved to 57.4% on Math. DeepSeek Math RL7B fine-tuned with GRPO RL further improved performance to 88.2% on GSM 8K and 51.7% on Math. And as you can see in the table, they are outperforming all open source models from 7B to 70B. And lastly, the GRPO RL methods improve major weighting accuracy, making the model more consistent in math. As seen in the figure, archive-only corpora like MathPal do not improve math reasoning, unlike the DeepSeek math corpus, which leads to consistent improvements across all benchmarks. As you can see in the table, the RL fine-tuning provides a significant boost in performance, especially with tools.
Hi, I'm Tei Cheng. So first, I'll discuss the lessons learned from the pre-training stage of DeepSeek Math. The team discovered that code training significantly improves reasoning, and by teaching the model Python before math, it developed better logical and step-by-step thinking. Next, a two-stage training approach where the code comes first and math comes second has produced strongest reasoning ability. And they also found that missing code and math data help prevent the model from forgetting its coding skills. However, training on scientific papers didn't really help much, and instead, real-world math data on the web turned out to be much more effective. Next, the authors introduced a new reinforcement learning algorithm called group relative policy optimization. So compared to the traditional PPO method, this method is simpler and more efficient as it doesn't need a separate critic model. So it uses less memory and computes faster. It works by letting the model compete with its own answers and learn which ones performs better. And as a result, the model's accuracy has increased. While from the dataset of GSM 8K improved from 82.9 to 88.2%, and on the math dataset from 46.8 to 51.7%. In evaluating DeepSeek Math, there are several strengths and weaknesses, and among its strengths, the GRPO algorithm is a major innovation that makes reinforcement learning both effective and efficient, and it also used a large multilingual dataset of 120 billion math tokens and proved that code training leads to measurable reasoning gains. However, the model still has weaknesses as it performs poorly in geometry and theorem-proof tasks. It depends heavily on web data, and its smaller 7 billion parameter size limits few-shot learning. To conclude our presentation here today, DeepSeek Math shows that smart training matters more than model size. Its combination of code and math data together with the new GRPO algorithm, sets a strong foundation for future open-source math reasoning models. While it still needs to grow in geometry and real-world generalization, it's a very clear example that smaller, well-trained models can perform impressively and almost matching all the large proprietary systems like GPT-4 and Gemini Ultra. Thank you. That's the end of our presentation.